A titration is used to determine the molarity of an acid or base in a solution. In a titration, you generally use a burette, and you put your known pH in that burette. Then, in an Erlenmeyer flask or a beaker or some type of container, we have an unknown pH that we're dropping the known pH into. A useful unit that we use in titration is a millimole. Milli, just like milligram, is 1,000th of a mole. So we use our lowercase m and then mole. So just like molarity is moles per liter, we can also use millimoles per milliliter gives you molarity. So our 2 millis would cancel, giving me molarity. You don't have to use millimoles, so you can just use moles and liters, but it is a useful unit in titrations because we're going to be using such small amounts of acid and base. It makes your numbers more user-friendly. So millimoles divided by milliliters gives you molarity. The equivalence point is an important definition. It's the point in the titration where the amount of acid or base has been added to exactly react with all the base or acid originally present. In other words, your moles of acid will equal the moles of base at the equivalence point. So here we have a burette, and inside that burette we have some sodium hydroxide. Our sodium hydroxide is a strong base, so it's separated into sodium and hydroxide ions. And inside of our beaker below, we're going to put some hydrochloric acid. Is this a good representation for hydrochloric acid? What do you think? If you said no, you're correct. This is a strong acid, and so strong acids should be dissociated 100%. So we should have hydrogen ions and chloride ions in solution. Before we open up the burette and start letting in some sodium hydroxide, we should probably add an indicator as well. We can use indicators. We can also use pH probes to measure the pH during the titration. In this case, our indicator is colorless in an acidic solution and pink in a basic solution. So before we begin, let's take our pH of the solution. If we were to measure the pH, notice the only thing affecting pH is our hydrogen ions. So before the reaction begins, only a strong acid is present, and therefore the pH will depend only on that strong acid. So we can simply find the pH by doing the negative log of whatever that concentration of our original acid was. Now, if we open up the burette and start letting in some sodium hydroxide, the sodium would react with chlorine and the hydroxide would react with hydrogen ions. But sodium chloride is a soluble salt, so it's going to stay dissociated, while hydrogen and hydroxide go together to make water. If we let in another one, again, our sodium would stay apart and our hydrogen would combine with our hydroxide to make water. So at this point, we are in this middle section of the graph. We're halfway to neutralizing all of our acid. But again, we only have a strong acid present, and so our pH will depend just on the concentration of the remaining hydrogen ions. So pH is equal to negative log of hydrogen remaining. If we keep adding sodium hydroxide, At this point, we have neutralized all of the hydrogen ions. We no longer have any hydrogen ions remaining. This is the equivalence point. Notice we have water and we have a neutral salt. On the titration curve, we're right here in the middle of this steep vertical line. So the equivalence point, again, is when moles of acid equal moles of base. We've completely neutralized the acid. Since only water and a neutral salt remain, our pH is 7. You can see that over here on the graph. But what if we keep adding sodium hydroxide? We still have some in the burette. So if we pull in our remaining sodium hydroxide, our sodium stays a spectator ion, but our hydroxide doesn't have any hydrogen ions to react with it and neutralize it. Therefore, my solution turns basic. We can see that with our indicator that's now purple or pinkish purple. So at this point, we are past the equivalence point. When you are past the equivalence point, the pH depends only on the excess item that was in the burette. In this case, our excess strong base. So we would first find our pOH based on how many hydroxides are in solution, and then we can find our pH by subtracting from 14. So again, past the equivalence point, you're going to have some unreacted hydroxide ions. If you have a strong acid by strong base titration. And again, your curve would look like this, where we're starting in an acidic pH and we're going up to a basic pH. But what if we don't have a strong acid and we start with a weak acid? So here we have our burette. It's filled with our sodium hydroxide still, but in the bottom we have HF. So is this the correct way to represent our HF? You said no, you are correct, but is this the correct way of representing HF? You said no again, you're still correct. HF is a weak acid, so only about 1 in 10 is going to break up. We're going to go in and have one broken apart since we should have some hydrogen ions and we're dealing with such a small number in our visualization here. So to begin with, before adding any of our base, first let's go in and add our indicator. And our pH is going to depend on the amount of hydrogen ions that are floating around in solution. But unlike a strong acid where I can just say, well, I had 4 moles or 4 molarity, let me just negative log that. I only have a weak acid present, so I've got to do a Rice table to find the pH of that weak acid based on its Ka value. The bigger the Ka value, the more that acid would break apart. But again, it's not going to break apart 100% because it's a weak acid. So now let's start adding some sodium hydroxide. So if we add in 1 sodium hydroxide, our sodium, just like before, is a spectator ion, and our hydroxide's not going to react with one of these because they're still together. It's going to react with this hydrogen that is dissociated from the fluorine. Just like before, our hydrogen and hydroxide make water. But now I don't have any hydrogens left apart. So the reaction is going to shift to the right, breaking up some of the H and F. When you remove a product, the reaction shifts to regain that product because our Q becomes too small, so the reaction has to shift right to produce more of that product. That's why more of the HF is going to break apart. So here, if we look at it, we have hydrogen ions, but we also have fluorine. And unlike chlorine, fluorine is the conjugate of HF. This is a weak acid Fluorine is a weak base because together they're conjugates. So I don't just have hydrogen ions, I have hydrogen, or I have a weak acid and a weak base. So that means I have a buffer. And so I can find my pH by doing the negative log of my Ka plus log of base over acid, or pKa plus log of base over acid. If I let in another sodium hydroxide, my sodium's a spectator, my hydroxide reacts with the hydrogen to produce water, and another HF is going to break apart at that point. At this point, we have 2 hydrogens left. At this point, we've neutralized half of our acid. And since we've neutralized half of our acid, we have a buffer still, but we're halfway to equivalence because we started with 4 acids. Now we only have 2 acids left. So we're halfway to equivalence. So pH will equal pKa because I have equal amounts of acid and my conjugate base. If we let in a couple more, sodium is a spectator, we make a water, another spectator, and another water. So in this case, we have no more hydrogen ions. All we have is fluorine ions. And we also have some sodium, but sodium is neutral. So the only one that's affecting our pH is fluorine. And we said earlier, fluorine is a weak base. So if you noticed, our indicator is now purple, or pinkish purple, because now we're basic. If we look at the graph, we're at the equivalence point. Equivalence point does not always mean that pH is 7. It simply means your moles of acid equal moles of base. At this point, only the conjugate of the weak acid remains, which is a base. So pH is above 7. We're going to do a Rice table to find the pH of the conjugate base. Again, it's a base, so pH should be above 7. But if we continue adding our NaOH, now we have OH and we have fluorine. Well, fluorine is a weak base and OH is a strong base. So our pH is only going to matter for the strong. Fluorine has to undergo a hydrolysis reaction with water to produce HF and hydroxide, while OH is already hydroxide. So when you have a strong base and you have a weak base, we're only going to care about the strong base. So any point past the equivalence point on a weak acid strong base titration, the pH will depend only on the strong base. So just like before, we can do the POH, or find our POH with the amount of hydroxide that was added that was extra, and then find our pH from there. So this one is a weak acid by a strong base. One more thing that you should add to your graph is from the very beginning, after you add a drop of the space to right before you reach the equivalence point, all of this is a buffer. But within that buffer, we said that at the halfway to equivalence point, pH equals pKa. Well, any point between where basically you started to right before that, pH will be less than pKa because we have more of the acid than the conjugate base. And then to right after the halfway to equivalence point, to right before the equivalence point, all of this, your pH is going to be greater than your pKa because you have more of the conjugate base than the acid.